In ancient mythology, Io was a priestess transformed by Zeus into a white heifer, forever wandering the earth in her altered form. When Galileo Galilei peered through his telescope 414 years ago and discovered Jupiter's innermost large moon, he unknowingly named a world that would prove far more transformative than its mythological namesake. This distant sphere of fire and ice has become humanity's window into volcanic processes beyond Earth, a natural laboratory where sulfur paints landscapes in yellows and oranges while mountains rise higher than Everest. The discovery and early observations. On the evening of January 7th, 1610, the cold winter air of Padua carried with it the promise of revelation. Galileo Galilei, professor of mathematics at the university, carefully positioned his hand-crafted telescope toward the brilliant beacon of Jupiter hanging in the darkness above. Through the modest 20-power magnification of his instrument, he observed something that would fundamentally alter humanity's understanding of the cosmos. 3 small points of light accompanied the giant planet, arranged in a nearly straight line through Jupiter's equatorial plane. The following night brought confusion and wonder in equal measure. The arrangement of these mysterious companions had changed. Where 3 had been visible before, now 4 appeared. Their positions shifted relative to Jupiter itself. Over successive nights of patient observation, Galileo meticulously recorded their movements, gradually recognizing a pattern that defied the geocentric model of the universe that had dominated Western thought for over 1,000 years. These were not distant stars accidentally aligned with Jupiter, but moons orbiting another world. The innermost of these 4 Medicean stars, as Galileo initially called them in honor of his patron Cosimo de' Medici, would later receive the name Io. This discovery represented far more than the addition of new celestial bodies to astronomical catalogues. It demonstrated definitively that not everything in the heavens revolved around Earth, providing crucial support for the Copernican model of the solar system. Simon Marius, a German astronomer observing independently, claimed to have discovered these moons slightly earlier than Galileo, though he published his findings later. It was Marius who suggested the names we use today, drawn from the mythological lovers of Zeus. Io, Europa, Ganymede, and Callisto became the designations for these 4 Galilean satellites, with Io being the innermost and most peculiar of them all. For nearly 3 centuries after its discovery, Io remained little more than a point of light, even through the most powerful telescopes. Astronomers could determine its orbital period of approximately 42.5 hours, making it the fastest orbiting of the Galilean moons. They calculated its distance from Jupiter at roughly 422,000 kilometers, placing it deep within the giant planet's gravitational embrace. Early spectroscopic studies in the late 19th and early 20th centuries hinted at unusual surface properties, but the technology of the time couldn't reveal the extraordinary nature of this distant world. The development of infrared astronomy in the 1960s brought the first hints of Io's volcanic character. Observations showed unusual heat signatures that puzzled researchers. Some scientists proposed that Io might possess a thin atmosphere, while others suggested the moon might be covered in salts or sulfur compounds. These early infrared studies detected temperatures that seemed inconsistent with a dead frozen world at Jupiter's distance from the Sun, but the true explanation remained elusive. Ground-based telescopes gradually improved throughout the 20th century, revealing tantalizing details about Io's appearance. Unlike the icy surfaces of Europa, Ganymede and Callisto, Io displayed a distinctly yellowish hue. Astronomers noticed that the moon's brightness varied slightly as it rotated, suggesting an uneven distribution of surface materials. Some observers reported seeing bright spots that appeared and disappeared, though these observations push the absolute limits of Earth-based telescopic resolution. The space age brought new possibilities for understanding Io. As NASA and other space agencies developed plans for exploring the outer solar system, Io featured prominently in mission objectives. Scientists recognized that understanding Jupiter's moons would provide crucial insights into the formation and evolution of the solar system. The peculiar spectroscopic signatures and unusual coloration of Io made it a particularly intriguing target for close-up investigation. In the early 1970s, technological advances in ground-based astronomy allowed for more detailed spectroscopic analysis of Io's surface. These studies revealed the presence of sulfur and sulfur dioxide, explaining the moon's distinctive coloration. However, the distribution and state of these materials remained mysterious. Some researchers proposed that Io might be covered in sulfur dioxide frost, while others suggested more exotic explanations for the observed spectra. The discovery of a sodium cloud surrounding Io in 1973 added another layer of mystery. Robert Brown, observing from Kitt Peak National Observatory, detected sodium D-line emission extending along Io's orbital path. This cloud formed a torus around Jupiter, suggesting that material was somehow escaping from Io's surface or atmosphere. The mechanism driving this escape remained unknown, though some scientists began to suspect that Io might be more geologically active than previously imagined. Theoretical work in the mid-1970s began to explore the possibility of tidal heating as an energy source for the Galilean moons. Stanton Peele, Patrick Casson, and Ray Reynolds published a groundbreaking paper in 1979, just days before Voyager 1's encounter with Jupiter, predicting that Io should be volcanically active due to tidal heating. Their calculations showed that the gravitational interactions between Io, Europa, and Ganymede, combined with Jupiter's immense gravity, should generate enough internal heat to melt Io's interior and drive volcanic activity. This theoretical prediction represented a revolutionary idea in planetary science. Prior to this work, most scientists assumed that small bodies far from the Sun would be geologically dead, their internal heat long since radiated away. The concept of tidal heating as a major energy source opened new possibilities for understanding not just Io, but potentially habitable environments throughout the solar system and beyond. As Voyager 1 approached the Jupiter system in early 1979, anticipation built within the scientific community. The spacecraft carried sophisticated cameras and instruments capable of revealing Io's surface in unprecedented detail. Mission planners scheduled numerous observations of all 4 Galilean moons, with particular attention paid to Io due to its unusual properties and the recent theoretical predictions of volcanic activity. The approach phase of Voyager 1's encounter provided increasingly detailed views of Io's surface. Even from millions of kilometers away, the images revealed a world unlike anything previously observed in the solar system. The surface displayed a remarkable palette of colors, dominated by yellows, oranges, and reds, with patches of white and black creating a complex mosaic. Most surprisingly, the images showed no impact craters, suggesting an extremely young and dynamic surface. Formation and birth in the Jovian system. 4.5 billion years ago, in the swirling disk of gas and dust that would become our solar system, the seeds of Io's creation were being sown. The solar nebula, a vast cloud of hydrogen, helium, and heavier elements left over from previous generations of stars, had begun its gravitational collapse. At the center of this maelstrom, the proto-sun was gathering mass and beginning its journey toward nuclear fusion. Further out in the disk, where temperatures were cooler and ices could condense alongside rocky materials, the giant planets were taking shape. Jupiter formed early and rapidly in the solar system's history, its massive gravity well acting like a cosmic vacuum cleaner, sweeping up gas and dust from the surrounding nebula. Within perhaps just a few million years, Jupiter had accumulated enough mass to dominate its region of the solar system, creating a miniature version of the solar nebula around itself. This circumplanetary disk, or subnebula, extended outward from the young giant planet, containing the raw materials from which its extensive moon system would emerge. The temperature gradient within Jupiter's subnebula played a crucial role in determining the composition of its forming moons. Close to the planet, where Io would eventually orbit, temperatures remained relatively high due to Jupiter's own heat of formation and the gravitational energy released by infalling material. These elevated temperatures meant that volatile compounds like water ice couldn't condense in the inner regions of the disk. Instead, the available building materials consisted primarily of rocky and metallic substances, including silicates, iron, and sulfur compounds. The process of moon formation within Jupiter's subnebula likely proceeded through stages of gradual accumulation. Initially, microscopic dust grains collided and stuck together through electrostatic forces, forming larger and larger aggregates. As these particles grew to pebble and boulder size, gravitational interactions became increasingly important. The disk's rotation caused material to concentrate in the equatorial plane, increasing the density and collision rate of particles. Within this dense midplane of the circumplanetary disk, gravitational instabilities began to develop. Regions of slightly higher density attracted more material, growing at the expense of their surroundings. These nascent moonlets, perhaps initially no larger than asteroids, continued to sweep up material from their orbital zones. The process of accretion was violent and chaotic, with countless collisions between growing bodies. Some impacts were gentle enough to allow merging, while others were catastrophic, shattering both impactor and target. Io's formation zone, being closest to Jupiter among the major moons, experienced unique conditions that would profoundly influence its composition and subsequent evolution. The intense radiation environment near Jupiter, combined with the planet's powerful magnetic field, affected the chemistry of the forming moon. Solar wind particles trapped in Jupiter's magnetosphere bombarded the inner disk, potentially altering the oxidation state of iron and other elements. These processes may have contributed to Io's unusual composition, particularly its apparent enrichment in sulfur relative to other rocky bodies. The timescale of Io's formation remains a subject of scientific debate, but models suggest it likely took between 100,000 and 10 million years for the Moon to reach approximately its current mass. During this period, the growing Moon would have been subjected to intense bombardment by remaining debris in the circumplanetary disk. The heat generated by these impacts, combined with the decay of radioactive elements incorporated during accretion, would have been sufficient to melt and differentiate Io's interior. Differentiation, the process by which denser materials sink toward the centre while lighter materials rise to the surface, was a crucial stage in Io's early evolution. Iron and iron sulfide, being the densest components, settled to form a metallic core. Estimates based on Io's observed density and moment of inertia suggest this core comprises approximately 20% of the Moon's radius. Above the core, a thick mantle of silicate rock formed, possibly with compositions similar to terrestrial peridotite or pyroxenite. The early Io likely possessed a magma ocean, a global layer of molten rock maintained by the tremendous heat of accretion and differentiation. This magma ocean phase would have lasted millions of years, during which volatile elements and compounds would have been efficiently separated and transported. Sulfur and sulfur compounds, being relatively volatile and less dense than silicate minerals would have tended to concentrate in the outer layers of the Moon. This early chemical stratification set the stage for Io's later evolution as the solar system's most volcanically active body. As Jupiter's subnebula dissipated and the flux of impacting material decreased, Io began to cool and solidify. However, unlike smaller bodies that would have quickly become geologically dead, Io's position in the Jupiter system ensured a continuous supply of internal heat through a mechanism that wouldn't be fully understood until billions of years later. The gravitational resonances with Europa and Ganymede were established early in the system's history, locking the three inner Galilean moons into an orbital dance that would keep Io's interior molten throughout the age of the solar system. The formation of Io's neighbouring moons played a crucial role in determining its fate. Europa, forming slightly farther from Jupiter where water ice could condense, accumulated a composition roughly half rock and half ice. Ganymede and Callisto, forming in progressively cooler regions of the subnebula, incorporated even higher proportions of ice. This compositional gradient among the Galilean moons provides important clues about conditions in Jupiter's early circumplanetary disk and helps constrain models of satellite formation around giant planets. The establishment of the Laplace resonance between Io, Europa, and Ganymede represents one of the most important events in Io's history. This resonance, in which Io completes 4 orbits for every 2 of Europa and every 1 of Ganymede, maintains orbital eccentricities that would otherwise be damped by tidal dissipation. The resonance likely formed through orbital migration, driven by tidal interactions with Jupiter, possibly within the first 100 million years of the Moon's existence. Once established, this resonance became the engine driving Io's perpetual volcanic activity. Evidence from the lunar samples, returned by Apollo missions and meteorites, suggests that the inner solar system experienced a period of heavy bombardment between 4.1 and 3.8 billion years ago. While direct evidence from the Jovian system is limited, Io likely experienced its share of this bombardment. However, unlike the heavily cratered surfaces of Ganymede and Callisto, any record of this ancient bombardment on Io has been completely erased by subsequent volcanic activity. The Moon's surface, as we see it today, is geologically young, continuously renewed by volcanic processes. The early history of Io's atmosphere, if one existed during its formation and early evolution, remains highly uncertain. Any primordial atmosphere acquired during accretion would have been subject to intense erosion by Jupiter's magnetosphere and solar radiation. The establishment of volcanic activity early in Io's history would have begun the process of volcanic outgassing that maintains the tenuous atmosphere observed today. This atmosphere, composed primarily of sulfur dioxide with trace amounts of sulfur monoxide and other species, represents a balance between volcanic supply and loss to space. Physical characteristics and unique properties. Io stands as the 4th largest moon in our solar system, with a mean radius of 1,821.6 kilometers, making it slightly larger than Earth's moon. This dimension places Io in the company of worlds large enough to have achieved hydrostatic equilibrium, moulding themselves into nearly spherical shapes under their own gravity. Yet despite this respectable size, Io's characteristics diverge dramatically from what we might expect of a moon orbiting in the cold depths of the outer solar system. The moon's mass, approximately 8.93 times 10 to the 22nd kilograms, combines with its volume to yield a bulk density of 3,528 kilograms per cubic meter. This high density immediately sets Io apart from its Galilean siblings and most other moons in the outer solar system. While Europa, Ganymede, and Callisto show decreasing densities with distance from Jupiter, reflecting increasing proportions of water ice in their compositions, Io's density suggests a predominantly rocky composition with a significant metallic core. The internal structure of Io, as revealed through careful analysis of its gravitational field and response to Jupiter's tides, consists of distinct layers that speak to a complex history of differentiation and ongoing geological activity. At the Moon's heart lies a core of iron or iron sulfide, extending to roughly 900 kilometers from the center. This core, which may be partially molten, accounts for approximately 20% of Io's total radius. The presence of sulfur in the core forming iron sulfide compounds would lower the melting temperature significantly compared to pure iron, potentially allowing the core to remain at least partially liquid despite Io's relatively small size. Surrounding this metallic heart, a vast mantle of silicate rock extends outward for approximately 900 additional kilometers. This mantle, composed primarily of magnesium-rich silicates, similar to Earth's upper mantle, exists in a state of partial melt. Current models suggest that perhaps 20% or more of the mantle consists of molten rock, forming vast underground magma reservoirs that feed the Moon's prolific volcanic activity. The exact degree of melting varies with depth and location, influenced by the complex patterns of tidal heating that warm Io from within. The outermost layer, Io's lithosphere, or rigid outer shell, measures perhaps 30 to 50 kilometers in thickness, though this value likely varies considerably across the Moon's surface. This relatively thin lithosphere floats atop the partially molten interior, frequently punctured by ascending magma that erupts through hundreds of volcanic centers scattered across the surface. The lithosphere itself appears to consist of silicate rocks overlain by extensive deposits of sulfur and sulfur compounds, creating the colorful palette that makes Io instantly recognizable. Temperature variations across Io's surface create a world of extreme contrasts. The average surface temperature hovers around negative 130 degrees Celsius, cold enough to freeze sulfur dioxide into a solid frost. Yet volcanic hotspots punctuate this frozen landscape, with temperatures exceeding 1,300 degrees Celsius, hot enough to melt silicate rock. Some measurements of active lava flows have recorded temperatures approaching 1,600 degrees Celsius, among the hottest surface temperatures measured anywhere in the solar system. These extreme temperature variations drive complex cycles of sublimation and condensation across Io's surface. Sulfur dioxide frost deposited on the cold night side or in permanently shadowed regions sublimates rapidly when exposed to sunlight or volcanic heat, creating transient atmospheric plumes that can extend hundreds of kilometers above the surface. This constant cycling of material between solid and gaseous states contributes to the rapid resurfacing that keeps Io's surface perpetually young. The Moon's rotation tidally locked to Jupiter in a one-to-one resonance means that one hemisphere permanently faces the giant planet, while the opposite hemisphere always faces away. This synchronous rotation, completed once every 42.5 hours, creates distinct leading and trailing hemispheres as Io orbits Jupiter. The leading hemisphere, which faces forward in the direction of orbital motion, shows subtle differences in composition and appearance compared to the trailing hemisphere, possibly due to differential rates of particle bombardment from Jupiter's magnetosphere. Io's orbit traces an elliptical path around Jupiter with an eccentricity of 0.0041, small by the standards of many solar system bodies, but crucial for the Moon's geological activity. This slight deviation from a perfect circle means that Io's distance from Jupiter varies by about 3,500 kilometers between closest and farthest approach. While this might seem insignificant compared to the mean orbital distance of 421,800 kilometers, the varying gravitational force creates the tidal flexing that powers Io's volcanism. The Moon's orbital inclination of 0.036 degrees keeps it very close to Jupiter's equatorial plane, ensuring that Io spends most of its orbit within the intense radiation environment of Jupiter's inner magnetosphere. This location subjects the Moon to a constant bombardment of charged particles, primarily electrons and ions, travelling at significant fractions of the speed of light. The radiation environment around Io is so intense that it would deliver a lethal dose to an unprotected human in a matter of minutes. Io's interaction with Jupiter's magnetosphere creates a complex electromagnetic environment unique in the solar system. As the Moon orbits through Jupiter's magnetic field lines, it generates an electrical current system of approximately 5 million amperes. This current flows along magnetic field lines, connecting Io to Jupiter's polar regions, creating brilliant auroral displays in Jupiter's atmosphere at the magnetic footpoints of these flux tubes. The power dissipated in this circuit, roughly 2 trillion watts, represents one of the most powerful electrical systems in the solar system. The Moon's surface gravity, approximately 1.8 meters per second squared, or about 18% of Earth's gravity, is sufficient to retain a tenuous atmosphere, but not strong enough to hold on to lighter gases for geological timescales. This relatively weak gravity, combined with the low escape velocity of 2.56 kilometers per second, means that volcanic eruptions can easily launch material high above the surface, with some volcanic plumes reaching heights of 500 kilometers or more. The albedo, or reflectivity, of Io's surface varies dramatically depending on the composition of surface materials. Fresh sulfur dioxide frost reflects about 65% of incident sunlight, appearing bright white in images. In contrast, dark pyroclastic deposits and certain sulfur allotropes absorb most incoming light, creating patches with albedos as low as 5%. The Moon's overall geometric albedo of approximately 0.63 makes it one of the brighter objects in the Jupiter system, despite the prevalence of dark volcanic materials. Spectroscopic observations reveal a surface dominated by sulfur in various allotropes and oxidation states, sulfur dioxide in both frost and gaseous forms, and smaller amounts of sulfur monoxide and disulfur monoxide. The different allotropes of sulfur, which form at different temperatures, create much of Io's spectacular colour palette. Bright yellow areas contain ordinary orthorhombic sulfur, while orange and red regions host sulfur that has been heated and rapidly cooled, creating metastable forms that slowly revert to yellow over time. White regions are typically sulfur dioxide frost, while black areas often indicate recent, still warm, silicate lava flows. The absence of water ice on Io's surface, in stark contrast to the other Galilean moons, reflects both the Moon's formation in the warm inner region of Jupiter's subnebula and the efficiency with which any water would be lost from the surface. Any water molecules released by volcanic activity or delivered by cometary impacts would quickly dissociate under the intense radiation environment, with the hydrogen escaping to space and the oxygen potentially combining with sulfur to form sulfur oxides. The volcanic wonderland, active geology. No other world in our solar system presents such a spectacular display of ongoing geological activity as Io, where hundreds of volcanoes reshape the landscape in real time, creating a surface younger than any other planetary body we've observed. The discovery of active volcanism on Io in 1979 revolutionized our understanding of planetary geology, demonstrating that worlds far from the sun's warmth could maintain geological activity through alternative energy sources. The mechanism driving Io's volcanism differs fundamentally from the plate tectonics and mantle convection that power Earth's volcanic activity. Instead, Io's internal heat comes from tidal flexing, a process that kneads the moon's interior like cosmic bread dough. As Io follows its slightly elliptical orbit around Jupiter, the varying distance to the giant planet causes the strength of Jupiter's gravitational pull to fluctuate. When Io approaches Jupiter at perapsis, the stronger gravitational force stretches the moon along the Jupiter-facing axis. As it recedes to apopsis, this deformation relaxes, only to begin again with the next orbital cycle. This rhythmic deformation, occurring every 42.5 hours, would typically circularize an orbit through tidal dissipation, eventually eliminating the source of heating. However, Io's orbital resonance with Europa and Ganymede prevents this circularization, maintaining the eccentricity that drives the tidal heating. The amount of energy generated through this process is staggering, estimated at roughly 100 trillion watts, or about 2.5 watts per square metre, averaged over Io's entire surface. This heat flow exceeds Earth's average heat flow by a factor of 30, despite Io being much smaller than our planet. The distribution of tidal heating within Io remains an active area of research, with different models predicting various patterns of heat generation. Early models suggested that heating would be concentrated in the deep interior, but more recent work indicates that dissipation in a partially molten upper mantle might dominate. The pattern of volcanic activity on Io's surface provides crucial constraints on these models, with the observed distribution of hotspots suggesting that heat generation peaks at relatively shallow depths, perhaps 50 to 100 kilometers below the surface. Volcanic eruptions on Io take several distinct forms, each contributing to the moon's ever-changing landscape. Basaltic eruptions, similar in composition to those at Hawaii or Iceland on Earth, produce dark, silicate-rich lava flows that can extend for hundreds of kilometers across the surface. These flows, with temperatures exceeding 1,200 degrees Celsius, initially appear black or dark brown, but gradually brighten as they cool and become coated with sulfur and sulfur dioxide from the moon's atmosphere and neighbouring eruptions. The most visually spectacular volcanic features on Io are the towering plume eruptions that can launch material 500 kilometres or more above the surface. These plumes, driven by the explosive vaporization of sulfur dioxide as magma encounters near-surface volatile deposits, create umbrella-shaped fountains of gas and particles that settle in vast ring deposits around their source vents. The Tvashtar-Pateri eruption, observed by the New Horizons spacecraft, in 2007 produced a plume reaching 330 kilometers in altitude, with particles following ballistic trajectories in Io's weak gravity before settling hundreds of kilometers from the vent. Prometheus-type plumes represent a unique category of volcanic activity found nowhere else in the solar system. These long-lived plumes, which can persist for decades, form when active lava flows encounter sulfur dioxide frost deposits. The heat from the advancing flow front vaporizes the frost, creating a sustained plume that appears to wander across the surface as the flow advances. The Prometheus plume itself has been observed continuously since the Voyager encounters in 1979, making it one of the longest observed extraterrestrial volcanic features. The morphology of volcanic constructs on Io differs markedly from typical terrestrial volcanoes. Instead of the steep-sided cones common on Earth, Io's volcanoes often form broad, low-relief features known as paterae. These irregular depressions, typically tens of kilometers across and hundreds of meters deep, may form through a combination of processes including explosive eruption, collapse following magma withdrawal, and sapping by sulfur dioxide sublimation. Many pateri contain active lava lakes, vast pools of molten rock that periodically overflow their confining walls to send flows spreading across the surrounding plains. Loki Patera, the most powerful persistent volcanic center on Io, exemplifies the scale of volcanic activity on this moon. This horseshoe-shaped depression, roughly 200 kilometers across, contains a lava lake larger than Lake Ontario on Earth. The lake undergoes periodic overturning events approximately every 475 Earth days, during which cool crust founders into the underlying magma, triggering a wave of resurfacing that propagates around the Patera at rates of 1 to 2 kilometers per day. During these events, Loki can radiate more than 10 trillion watts of thermal energy, making it temporarily the most powerful volcanic heat source in the solar system. The chemistry of Io's volcanism creates a unique interplay between silicate and sulfur volcanism. While the high-temperature eruptions clearly involve silicate magmas similar to terrestrial basalts, sulfur and sulfur compounds play crucial supporting roles. Sulfur dioxide acts as a volatile component, driving explosive eruptions much as water vapor does on Earth. Liquid sulfur, with its relatively low melting point of 115 degrees Celsius, can form secondary flows that emerge from cooling silicate lavas or erupt independently from dedicated sulfur volcanoes. The colors of fresh volcanic deposits provide insights into eruption temperatures and compositions. Black flows indicate high-temperature silicate lavas that haven't yet accumulated sulfurous coatings. Red deposits suggest sulfur that has been heated above 200 degrees Celsius, creating metastable polymers that gradually revert to yellow. White areas typically indicate fresh sulfur dioxide frost, either condensed from volcanic plumes or deposited during the cold Ionian night. Mountains on Io, some reaching heights of 18 kilometers above the surrounding plains, represent another puzzling aspect of the moon's geology. These structures, far taller than any mountains on Earth relative to the planet's radius, don't appear to be volcanic constructs. Instead, they may form through compressive tectonics as subsidence around volcanic centers creates lateral forces that squeeze and uplift crustal blocks. The extreme heights achieved by these mountains may be possible because Io's lithosphere, supported by a partially molten interior, can maintain steeper slopes than would be stable on a completely solid world. The rate of volcanic resurfacing on Io exceeds that of any other known planetary body. Based on the complete absence of impact craters and observations of surface changes between spacecraft visits, scientists estimate that Io's surface is completely renewed on timescales of roughly 1 million years. This corresponds to a global resurfacing rate of approximately 1 centimetre per year, though local rates near active volcanic centres can be much higher. Some active flows have been observed to advance at rates of hundreds of metres per day. Heat pipe volcanism, a theoretical mechanism proposed for Io, might explain some of the moon's unusual volcanic characteristics. In this model, vertical channels of ascending magma efficiently transport heat from the interior to the surface, bypassing the need for mantle convection. These heat pipes could maintain themselves through a positive feedback loop, where ascending magma melts surrounding rock, creating more magma that continues to rise. This mechanism might explain the apparent concentration of volcanism at discrete centres rather than along linear rift zones as seen on Earth. The global distribution of volcanic centres on Io shows intriguing patterns that provide clues about interior processes. Hotspots appear more concentrated at low latitudes, with fewer active centres near the poles. This distribution might reflect patterns of tidal heating, with more energy dissipated in equatorial regions. Additionally, there appears to be a slight concentration of volcanic activity in the sub-Jupiter and anti-Jupiter hemispheres, the points that experience maximum tidal flexing during each orbit. Observations of Io's volcanic activity over multiple decades have revealed both persistent and episodic behavior. While some volcanic centers like Loki and Prometheus maintain relatively steady activity for decades, others exhibit dramatic outbursts followed by periods of quiescence. The Surt eruption observed in 2001 produced one of the largest volcanic events ever witnessed in the solar system, with an eruption rate estimated at 10,000 cubic meters per second, covering an area of 1,900 square kilometers with fresh lava in a matter of days. Tidal heating and the dance with Jupiter. The extraordinary volcanic activity that defines Io's character springs from a cosmic dance of gravity and orbital mechanics that has persisted for billions of years. This gravitational choreography, involving Jupiter and Io's fellow Galilean moons, generates the internal heat that keeps Io's interior molten and drives the most prolific volcanism in the solar system. Understanding this process requires delving into the subtle interplay of celestial mechanics that transforms orbital energy into geological activity. At the heart of Io's tidal heating lies its orbital resonance with Europa and Ganymede, a mathematical relationship of profound consequence for all three moons. For every single orbit Ganymede completes around Jupiter, Europa circles twice, and Io races around 4 times. This precise 1:2:4 ratio, known as the Laplace resonance after the mathematician who first studied such systems, represents more than a numerical curiosity. It creates a self-reinforcing dynamic that has maintained itself for eons and will likely continue for billions of years to come. The resonance works through gravitational perturbations that occur at regular, predictable intervals. Every time Io overtakes Europa in their orbital race around Jupiter, which happens at the same point in Io's orbit due to the resonant relationship, Europa's gravity gives Io a small tug. Similarly, Europa receives regular gravitational kicks from both Io and Ganymede. These repeated perturbations at consistent orbital locations prevent the moon's orbits from becoming perfectly circular, maintaining small but crucial eccentricities that would otherwise decay through tidal friction. Without this resonance, tidal forces would gradually circularize Io's orbit, eliminating the varying distance from Jupiter that drives the tidal flexing. The moon would cool, solidify, and become another dead world like Earth's moon. Instead, the resonance maintains Io's orbital eccentricity at about 0.004, seemingly tiny but sufficient to vary Io's distance from Jupiter by roughly 3,500 kilometers during each orbit. This variation might appear negligible compared to the 422,000 kilometer average distance, but its effects are profound. The physics of tidal deformation follows from the inverse cube relationship of tidal forces with distance. As Io approaches periapsis, its closest approach to Jupiter, the giant planet's gravity pulls more strongly on the near side of Io than the far side. This differential force, or tidal force, stretches Io along the Jupiter-facing axis, while compressing it along perpendicular directions. The solid body of Io deforms into a triaxial ellipsoid, with the long axis pointing toward Jupiter. If Io's orbit were perfectly circular, this deformation would remain constant, with the same hemisphere always facing Jupiter due to tidal locking. The moon would assume an equilibrium shape, and no further heating would occur. However, the orbital eccentricity maintained by the resonance means that Jupiter's gravitational force varies throughout each orbit. As Io moves from periapsis to apoapsis, the tidal bulge must adjust to the changing gravitational field, but it cannot do so instantaneously. The solid rock of Io's interior possesses finite rigidity and viscosity, meaning it resists deformation and cannot respond immediately to changing forces. As the required shape of the tidal bulge changes faster than the rock can deform, internal friction develops. Different layers of the Moon experience shear stress as they attempt to adjust to the changing tidal forces. This friction converts orbital energy into heat, warming Io's interior in a process analogous to how repeatedly bending a wire coat hanger causes it to warm at the bend point. The magnitude of this tidal flexing is remarkable. Io's surface rises and falls by approximately 100 meters during each orbital cycle, a deformation that would be catastrophic on Earth but represents routine behavior for Io. For comparison, Earth's solid body tides caused by the Moon amount to only about 30 centimeters. The energy dissipated through this process is enormous, roughly 100 trillion watts, making Io by far the most geologically active body in the solar system relative to its size. The distribution of tidal heating within Io depends on the Moon's internal structure and the rheological properties of its materials. Early models assumed that most heating would occur in a solid mantle through viscoelastic dissipation. However, the discovery that Io likely contains a partially molten layer, a magma ocean comprising perhaps 20% liquid, changed these predictions dramatically. Fluid layers can dissipate tidal energy very efficiently through viscous friction, potentially concentrating heat generation in the upper mantle rather than distributing it throughout the Moon's interior. The presence of this partial melt layer creates a feedback mechanism that helps regulate Io's thermal state. As tidal heating increases, more rock melts, creating a less viscous layer that dissipates energy more efficiently. This enhanced dissipation generates more heat, potentially melting more rock. However, if too much melting occurs, the layer becomes so fluid that it deforms easily without generating much friction, reducing the heating rate. This self-regulating process may help maintain Io in a steady state with consistent levels of volcanic activity over geological time. The pattern of tidal heating varies across Io's interior in complex ways that scientists are still working to understand fully. Models suggest that heating should be strongest near the equator and weakest at the poles, consistent with the observed concentration of volcanic activity at low latitudes. The heating pattern also varies with depth, potentially creating distinct thermal boundary layers that influence where magma generation occurs and how it ascends to the surface. Jupiter's immense gravity creates more than just the primary tidal bulge on Io. Higher-order harmonics in the tidal potential create additional, smaller-scale deformations that contribute to the overall heating pattern. These complex tidal modes can focus energy dissipation in particular regions, potentially explaining why some areas of Io show concentrated volcanic activity, while others remain relatively quiet. The role of Io's core in tidal dissipation remains uncertain but potentially significant. If the core contains iron sulfide rather than pure iron, its melting temperature would be considerably lower, possibly allowing it to remain partially liquid. A fluid outer core would respond to Jupiter's changing gravitational field through a process called gravitational coupling, where the liquid attempts to maintain its equilibrium shape as the solid mantle deforms around it. This differential motion between core and mantle could generate additional heat through viscous friction at the core-mantle boundary. The orbital evolution of the Laplace resonance system continues today, albeit at an imperceptibly slow rate. Tidal dissipation in Io removes energy from the orbital system, which would normally cause Io's orbit to decay toward Jupiter. However, the resonance transfers angular momentum from the outer moons to Io, maintaining its orbit against this decay. Meanwhile, tidal interactions between the moons and Jupiter slowly push all three satellites outward, though this migration occurs at rates of only centimetres per year. The long-term stability of the Laplace resonance has profound implications for Io's geological history. Models suggest that the resonance has persisted for most of the solar system's history, meaning Io has experienced continuous volcanic activity for billions of years. This extended period of activity has allowed Io to process its entire inventory of volatile elements multiple times, creating the sulfur-rich world we observe today through cycles of volcanic outgassing, atmospheric escape, and surface condensation. Variations in the amplitude of tidal heating over different timescales add complexity to Io's thermal evolution. On the shortest scale, the 42.5-hour orbital period creates the basic heating cycle. However, longer period variations arise from the slow precession of Io's periapsis, the gradual change in the orientation of its elliptical orbit. This precession, with a period of roughly 350 years, modulates the efficiency of tidal heating and might contribute to long-term variations in volcanic activity. The interaction between tidal heating and Io's physical properties creates fascinating feedback loops that influence the moon's evolution. As rock heats and approaches its melting point, its viscosity decreases dramatically, allowing more efficient tidal dissipation. This enhanced heating can trigger runaway melting in localized regions, potentially explaining the formation of volcanic centers. Conversely, areas that cool and solidify become more rigid, dissipating less energy and potentially remaining volcanically inactive for extended periods. The three-body dynamics of the Laplace resonance create subtle but important effects on tidal heating patterns. The gravitational perturbations from Europa and Ganymede not only maintain Io's orbital eccentricity, but also induce small periodic variations in that eccentricity. These variations, occurring over timescales of years to decades, might modulate the intensity of tidal heating and could potentially trigger episodic volcanic events when heating exceeds critical thresholds. Studies of tidal dissipation in laboratory materials under conditions approaching those in Io's interior provide crucial constraints on heating models. Experiments show that partially molten rock exhibits complex rheological behavior, with viscosity depending strongly on temperature, pressure, melt fraction, and strain rate. These dependencies create non-linear responses to tidal forcing that can focus dissipation in unexpected ways, potentially explaining some of the puzzling aspects of Io's volcanic distribution. The efficiency of tidal heating in Io far exceeds that in any other known planetary body, making it a unique natural laboratory for studying this process. Earth experiences tidal heating from the Moon and Sun, but the energy dissipated amounts to only about 3 terawatts, mostly in the oceans rather than solid Earth. Europa likely experiences tidal heating as well, possibly maintaining a subsurface ocean, but at levels perhaps 100 times lower than Io. This range of heating rates among the Galilean moons provides valuable comparative data for understanding how tidal dissipation depends on composition, internal structure, and orbital configuration. Surface features and geographical regions. The landscape of Io presents a geographical diversity that rivals any terrestrial planet, with the volcanic plains, towering mountains, vast calderas, and active lava lakes creating a surface that changes measurably on timescales of weeks to years. Unlike the ancient cratered terrains that dominate most solid bodies in the solar system, Io's surface tells a story of ongoing creation and destruction, where new volcanic deposits constantly bury older features in an endless cycle of resurfacing. The most prominent surface features on Io are the hundreds of volcanic centers scattered across its surface, each with its own distinctive characteristics and eruptive style. These volcanic centers, formerly catalogued using names from mythologies worldwide, range from simple dark spots marking recent eruptions to complex multi-ringed structures hundreds of kilometers across. The International Astronomical Union has officially named over 400 features on Io, with active volcanic centers receiving names from fire, sun, thunder, and volcano deities, while mountains bear names from mythological locations associated with the underworld. Loki Patera, located at 13 degrees north latitude and 309 degrees west longitude, dominates Io's volcanic hierarchy as the most powerful, persistent heat source. This massive depression, shaped like an enormous horseshoe 200 kilometers across, contains a lava lake that periodically overturns in spectacular resurfacing events. During quiescent periods, a dark crust forms on the lake's surface, gradually thickening and cooling. When this crust becomes gravitationally unstable, it founders into the underlying magma, triggering a wave of fresh lava that propagates around the patera at speeds of 1 to 2 kilometers per day. The Prometheus volcano, nicknamed the Old Faithful of the Outer Solar System for its persistent activity, has maintained a relatively constant eruption for at least 40 years of observation. Located at 2 degrees south latitude and 154 degrees west longitude, Prometheus exhibits a unique eruption style where an insulated lava flow travels roughly 90 kilometers from its source before encountering sulfur dioxide frost plains. The interaction between the hot lava and volatile rich surface materials creates a sustained plume that rises about 100 kilometers above the surface, depositing a distinctive ring of bright and dark materials around the flow front. Pele, situated at 19 degrees south latitude and 257 degrees west longitude, represents another category of Io's volcanic features. This volcano produces some of the tallest volcanic plumes observed on Io, reaching heights of 300 kilometers or more. The Pele plume deposits form a distinctive red ring, roughly 1,000 kilometers in diameter, created by sulfur compounds that condense from the plume as it falls back to the surface. The color and extent of this deposit change over time, providing insights into variations in eruption intensity and gas composition. The Tvashtar Katina, a chain of volcanic craters at 60 degrees north latitude and 120 degrees west longitude, showcases the diversity of volcanic processes on Io. This region has produced some of the most spectacular eruptions observed by spacecraft, including a curtain of lava fountains 25 kilometers long, captured by the Galileo spacecraft, and a massive plume eruption, witnessed by New Horizons during its Jupiter flyby in 2007. The variety of activity at Tvashtar suggests a complex subsurface plumbing system capable of producing different eruption styles. Mountains on Io reach extraordinary heights that seem to defy explanation given the moon's small size. Boussoul Montes, the tallest measured peak, towers 18.2 kilometers above the surrounding plains, significantly higher than any mountain on Earth when measured from base to summit. These mountains don't appear to be volcanic constructs, but rather massive blocks of Io's crust that have been uplifted and tilted through tectonic processes. The mechanism driving this mountain building remains debated, but likely involves compression caused by the subsidence of volcanic regions forcing adjacent crustal blocks upward. The distribution and morphology of Io's mountains provide clues about the moon's crustal dynamics. Many mountains show evidence of massive landslides and slope failures, with debris aprons extending tens of kilometres from their bases. The steep slopes, some approaching 40 degrees, push the limits of what rocky materials can support, suggesting that Io's mountains may be actively growing and collapsing in a continuous cycle. The concentration of mountains in certain regions, particularly away from major volcanic centres, hints at global-scale patterns of crustal stress and deformation. Plains regions on Io, occupying the areas between volcanic centres and mountain ranges, display a remarkable variety of colours and textures that reflect their complex depositional history. These plains consist of layered volcanic deposits, including lava flows, pyroclastic materials, and condensed volatiles from volcanic plumes. The interleaving of different materials creates a stratigraphy that, while impossible to study directly, can be partially deciphered through careful analysis of colour variations and overlapping relationships. The coloration of Io's surface provides a spectacular natural palette unmatched elsewhere in the solar system. Bright white areas typically indicate fresh sulfur dioxide frost, either recently condensed from the atmosphere or deposited by nearby volcanic plumes. Yellow regions contain ordinary orthorhombic sulfur, stable at Io's surface temperatures. Orange and red areas host metastable sulfur polymers created when liquid sulfur is heated above certain temperature thresholds and then rapidly cooled. Dark brown to black regions mark recent silicate lava flows that haven't yet accumulated bright sulfurous coatings. Patera structures, the irregular volcanic depressions that host many of Io's most active eruptions, exhibit remarkable diversity in size, shape, and activity level. These features range from simple circular depressions a few kilometres across to complex multi-lobed structures exceeding 200 kilometres in maximum dimension. Some paterae contain active lava lakes that glow brightly in infrared observations, while others appear to be extinct or dormant calderas partially filled with cooled lava flows and pyroclastic deposits. The floors of many paterae show evidence of dramatic changes between spacecraft observations, with new lava flows covering hundreds of square kilometres in matters of weeks or months. The Gishbar Patera, for example, changed from a bright, possibly sulfur dioxide-rich floor to a dark surface covered with fresh lava between Voyager and Galileo observations. These rapid changes demonstrate that even seemingly quiet volcanic centres can experience sudden, dramatic eruptions. Flow fields extending from volcanic centres create some of Io's most distinctive surface patterns. These flows, ranging from a few kilometres to over 300 kilometres in length, show complex morphologies including channels, flow lobes, and breakout points where lava escaped confinement to spread across surrounding plains. The longest observed flow, emanating from the Amirani volcano, extends roughly 300 kilometres and shows evidence of an active flow front that advanced throughout the Galileo mission observations. Bright halos surrounding many volcanic centres result from the continuous rain of sulfur dioxide and other volatiles expelled during eruptions. These halos, which can extend hundreds of kilometres from their source, create distinctive albedo patterns that help identify recently active volcanoes, even when direct observation of eruption is not possible. The size and brightness of these halos change over time as fresh deposits bury older materials or as sulfur dioxide frost sublimes during the Ionian day. The polar regions of Io exhibit distinct characteristics that set them apart from equatorial and mid-latitude areas. Volcanic activity appears less common at high latitudes, possibly reflecting patterns of tidal heating that concentrate energy dissipation near the equator. The poles also show evidence of enhanced sulfur dioxide frost deposition, creating brighter surfaces that may act as cold traps for volatiles migrating from warmer regions. Tectonic features on Io, while less prominent than volcanic structures, provide important insights into crustal processes. Linear scarps, grabens, and possible strike-slip faults have been identified in high-resolution images, suggesting that Io's lithosphere experiences significant horizontal and vertical motions. These tectonic features often appear to be related to nearby volcanic centers or mountains, indicating complex interactions between volcanism, mountain building, and crustal deformation. The absence of impact craters on Io's surface provides the strongest evidence for the Moon's extraordinary resurfacing rate. Not a single confirmed impact crater has been identified despite careful searching of high-resolution images. Given the flux of impactors in the Jupiter system, this absence implies that Io's entire surface is renewed on timescales of roughly 1 million years or less. This resurfacing rate, approximately 1 centimetre per year when averaged globally, exceeds that of any other known planetary body by orders of magnitude. Atmosphere and interactions with Jupiter's magnetosphere. Above Io's colourful volcanic landscape exists one of the most unusual atmospheres in the solar system, a tenuous envelope of sulfur dioxide and other volcanic gases that participates in a complex interaction with Jupiter's powerful magnetosphere. This atmosphere, roughly 1 billion times thinner than Earth's at sea level, nonetheless plays crucial roles in Io's geology, appearance, and contribution to the Jovian system. The processes that create, maintain, and erode this atmosphere provide insights into atmospheric physics under extreme conditions found nowhere else. The primary constituent of Io's atmosphere is sulfur dioxide, a gas that would be toxic to terrestrial life, but serves as the lifeblood of Io's atmospheric dynamics. Surface pressures range from about 1 nanobar in the warmest regions during local noon to essentially 0 in the coldest nightside areas. This dramatic variation reflects the delicate balance between volcanic outgassing, sublimation of surface frosts, and loss processes that constantly remove gas from the atmosphere. 2 primary mechanisms maintain Io's sulfur dioxide atmosphere against continuous erosion. Volcanic eruptions inject gas directly into the atmosphere, with major eruptions capable of increasing local atmospheric pressure by factors of thousands. Between eruptions, sublimation of sulfur dioxide frost provides a steady baseline atmosphere. During Io's day, when surface temperatures reach negative 130 degrees Celsius, sulfur dioxide ice sublimes directly into gas. At night, when temperatures plummet to negative 180 degrees Celsius, this gas condenses back onto the surface as frost. This daily cycle of sublimation and condensation creates an atmosphere that essentially breathes with Io's rotation. As the terminator sweeps across the surface every 42.5 hours, a wave of atmospheric collapse follows the sunset line, while atmospheric reformation follows sunrise. Observations during Jupiter eclipses, when Io passes through the giant planet's shadow, have captured this atmospheric collapse in real time, with the atmosphere shrinking to perhaps 20% of its sunlit extent within 2 hours of entering eclipse. The vertical structure of Io's atmosphere differs markedly from familiar planetary atmospheres. Without a stratosphere or other stable layers, the atmosphere extends upward, with an exponential decrease in density determined by the balance between thermal energy and Io's modest gravity. The scale height, the altitude over which atmospheric density decreases by a factor of E, measures roughly 10 to 15 kilometers, meaning the already tenuous surface atmosphere becomes even more rarefied at modest altitudes. Volcanic plumes create temporary, localized atmospheres that can exceed the background atmospheric density by many orders of magnitude. These plumes, rising hundreds of kilometers above the surface, consist of sulfur dioxide gas and entrained particles of sulfur and silicate dust. The largest plumes create umbrella-shaped canopies where gas and particles follow ballistic trajectories in Io's weak gravity before falling back to the surface. During their brief flight, these materials can interact with Jupiter's magnetosphere, contributing to the complex plasma environment around Io. The interaction between Io's atmosphere and Jupiter's magnetosphere represents one of the most dramatic and energetic processes in the solar system. Io orbits deep within Jupiter's magnetosphere, where the magnetic field strength exceeds 2,000 Gauss, roughly 4,000 times stronger than Earth's surface field. This magnetic field, rotating with Jupiter every 9.9 hours, sweeps past Io at a relative velocity of 57 kilometers per second, faster than Io's orbital velocity of 17 kilometers per second. This supersonic flow of magnetized plasma past Io creates a complex interaction region, analogous to, but far more extreme than, the solar wind interaction with planetary atmospheres. The flowing plasma, consisting primarily of sulfur and oxygen ions originating from Io itself, collides with Io's atmosphere and surface, sputtering away approximately 1 ton of material per second. This sputtered material becomes ionized and swept up by Jupiter's magnetic field, contributing to the Ioplasma torus. The Ioplasma torus, a donut-shaped cloud of ions and electrons centered on Io's orbit, represents one of the most distinctive features of the Jovian magnetosphere. This torus contains roughly 1 ton of plasma, continuously replenished by Io and gradually lost through various transport processes. The plasma temperature in the torus reaches 50 to 100 electron volts, equivalent to hundreds of thousands of degrees Celsius, maintained by energy input from Jupiter's rotating magnetic field. The composition of the plasma torus reflects Io's unusual chemistry. Sulfur and oxygen ions dominate, existing in various ionization states from singly ionized S+ and O+ to highly ionized S5+ and O3+. The relative abundances of these species provide insights into the energy balance and chemical processes occurring in the torus. Sodium and potassium ions, while less abundant, create spectacular emission features visible from Earth-based telescopes. Io's position within this hostile plasma environment drives fascinating electromagnetic phenomena. As Io moves through Jupiter's magnetic field, it generates an enormous electrical current system. The relative motion between Io and the magnetic field induces an electric field that drives currents estimated at 5 million amperes. These currents flow along magnetic field lines, connecting Io to Jupiter's ionosphere, creating the Io flux tube. The Io flux tube acts as an electromagnetic highway between Io and Jupiter, channeling energy and particles between the two bodies. Where these currents enter Jupiter's atmosphere near the magnetic poles, they create brilliant auroral emissions known as the Io footprint. This footprint appears as a bright spot in Jupiter's aurora, followed by a trailing tail created by particles that have bounced between Jupiter's hemispheres along magnetic field lines. The power dissipated in the Io-Jupiter current system amounts to roughly 2 trillion watts, making it one of the most powerful electrical circuits in the solar system. This energy ultimately comes from Jupiter's rotation, with the electromagnetic interaction gradually transferring angular momentum from Jupiter to Io. Over billions of years, this process has contributed to the outward migration of Io's orbit, though the effect is small compared to tidal interactions. Neutral atoms and molecules escaping from Io's atmosphere create extensive clouds that reveal the Moon's influence throughout the Jupiter system. The neutral sodium cloud, first discovered from Earth-based observations, extends along Io's orbital path in a banana-shaped distribution. This cloud, continuously replenished by atmospheric escape and sputtering, provides a tracer of the complex dynamics occurring in the Io-Jupiter system. The escape of atmosphere from Io occurs through multiple mechanisms, each contributing to the overall loss rate of roughly 1 ton per second. Thermal escape, or Jeans escape, allows the fastest moving molecules in the high-altitude atmosphere to exceed Io's escape velocity. Sputtering by magnetospheric particles physically knocks atmospheric molecules into space. Atmospheric stripping by the flowing plasma removes gas from the upper atmosphere. Volcanic eruptions can directly inject gas at speeds exceeding escape velocity. The fate of material lost from Io's atmosphere depends on its composition and the mechanism of escape. Neutral atoms and molecules initially follow ballistic trajectories, but eventually become ionized through electron impact or photoionization. Once ionized, particles become trapped by Jupiter's magnetic field and join the plasma torus. The residence time in the torus varies from days to months before particles are transported outward through interchange instabilities or lost through charge exchange reactions. Observations of Io's atmosphere across different wavelengths reveal its complex structure and dynamics. Ultraviolet observations detect emissions from oxygen and sulfur atoms, mapping the distribution of these species around Io. Infrared observations reveal sulfur dioxide absorption features and can detect volcanic gases during eruptions. Millimeter and submillimeter observations probe the atmospheric temperature structure and can detect minor species like sulfur monoxide and sodium chloride. The discovery of a sulfur monoxide atmosphere on Io added another layer of complexity to atmospheric models. This molecule, less abundant than sulfur dioxide but still significant, likely forms through photochemistry or volcanic processes. The relative abundance of SO to SO2 varies across Io's surface, and with time, potentially providing insights into volcanic gas compositions and atmospheric chemistry. Seasonal variations in Io's atmosphere, driven by the slight inclination of Jupiter's orbit, create subtle but measurable effects. As Jupiter's distance from the Sun varies by about 5% during its 12-year orbit, the solar heating of Io's surface changes correspondingly. These variations affect the sublimation rate of surface frosts, potentially modulating atmospheric density and the rate of atmospheric escape. The Voyager encounters and first close views, March 5, 1979, marked a transformative moment in our understanding of Io and the outer solar system, as NASA's Voyager 1 spacecraft made its closest approach to Jupiter, passing within 278,000 kilometers of the giant planet's cloud tops. Among the mission's many objectives, the investigation of Jupiter's 4 Galilean satellites ranked high in priority, with Io's unusual spectroscopic properties and theoretical predictions of volcanic activity generating particular interest among mission scientists. The Voyager 1 spacecraft, launched 18 months earlier, on September 5, 1977, carried a sophisticated suite of instruments designed to study the Jupiter system in unprecedented detail. The imaging system, consisting of narrow-angle and wide-angle cameras, could resolve features as small as 5 kilometers across on Io's surface during closest approach. Infrared and ultraviolet spectrometers would analyze surface composition and search for atmospheric emissions. The spacecraft's trajectory had been carefully designed to provide close encounters with Io and Ganymede, while maintaining the gravity assist needed to continue onto Saturn. As Voyager 1 approached the Jupiter system in January 1979, long-range observations began revealing Io's bizarre appearance. Unlike the icy cratered surfaces of Ganymede and Callisto visible in approach images, Io displayed a mottled, multicolored surface dominated by yellows, oranges, and reds. Most remarkably, even in images taken from millions of kilometers away, not a single impact crater could be identified on Io's surface, suggesting an extremely young and possibly active surface. The theoretical prediction of volcanic activity on Io, published by Stanton Peele, Patrick Casson, and Ray Reynolds in the journal Science just 3 days before Voyager 1's closest approach, had prepared the scientific community for the possibility of geological activity. However, the scale and intensity of what Voyager would discover exceeded even the most optimistic expectations. Their paper, based on calculations of tidal heating, concluded with the prescient statement that widespread and recurrent surface volcanism would occur on Io. On March 5th, as Voyager 1 flew past Io at a distance of 20,600 kilometers, its cameras captured images that would revolutionize planetary science. The surface appeared as a bizarre mosaic of colors and textures, with dark spots surrounded by bright halos, flow-like features, and irregularly shaped depressions. The complete absence of impact craters was confirmed, indicating a surface age of less than 1 million years. But the most spectacular discovery was yet to come. 3 days after the Jupiter encounter, as Voyager navigation engineer Linda Morabito processed images for optical navigation purposes, she made one of the most significant discoveries in planetary exploration history. In an image of Io silhouetted against the darkness of space, she noticed an unusual umbrella-shaped feature extending from the moon's limb. Initially wondering if this might be another moon behind Io, she quickly realized she was seeing something unprecedented: an enormous volcanic plume rising 300 kilometers above Io's surface. This discovery of active volcanism on Io sent shockwaves through the scientific community. Further analysis of Voyager images revealed 8 additional volcanic plumes active during the flyby, with heights ranging from 70 to 300 kilometers. The Pele plume, the feature Morabito had discovered, created a fountain of material that fell in a vast ring 1,000 kilometers in diameter. These eruptions were clearly ongoing, catching Io in the act of resurfacing itself through volcanic processes. The Voyager 1 infrared spectrometer detected numerous hotspots on Io's surface, with temperatures far exceeding what could be explained by solar heating alone. Some regions showed temperatures above 400 degrees Kelvin, with the hottest areas approaching 600 degrees Kelvin. These measurements provided the first direct evidence of the tremendous heat flow from Io's interior, confirming that tidal heating was indeed powering extensive volcanic activity. 4 months later, Voyager 2 arrived at Jupiter, following a different trajectory that brought it within 1,100,000 kilometers of Io. While this distance was too great for high-resolution surface imaging, Voyager 2 made crucial observations of how Io's volcanic activity had changed in the intervening months. Several volcanic centers showed clear evidence of new eruptions, with fresh dark deposits covering areas that had appeared bright in Voyager 1 images. Most dramatically, Voyager 2 observed that the Loki volcanic center had undergone a major eruption between the 2 spacecraft encounters. An area of approximately 10,000 square kilometers had been resurfaced with dark material, presumably fresh lava flows. The plume from Pele remained active, though its intensity had varied. Meanwhile, a plume at the Loki site that had been active during Voyager 1's flyby had ceased, demonstrating the episodic nature of some eruptions. The combined Voyager observations revealed the diversity of volcanic styles on Io. Some eruptions produced predominantly dark, presumably silicate-rich materials that created flow fields hundreds of kilometers long. Others erupted bright materials likely sulfur or sulfur dioxide, that formed extensive white or yellow deposits. The plume eruptions appeared to be driven by the explosive vaporization of sulfur dioxide, creating fountains of gas and particles that followed ballistic trajectories in Io's weak gravity. Temperature measurements from the Voyager infrared instruments suggested that at least some of Io's lavas were exceptionally hot, possibly exceeding 1,000 degrees Celsius. These temperatures pointed to silicate volcanism similar to basaltic eruptions on Earth, rather than the low-temperature sulfur volcanism that some scientists had initially proposed. The presence of both silicate and sulfur volcanism created a unique volcanic environment found nowhere else in the solar system. The Voyager missions also made the first detailed observations of Io's interaction with Jupiter's magnetosphere. The spacecraft detected a flux tube of electrical current connecting Io to Jupiter, confirming theoretical predictions of electromagnetic interactions. Measurements showed that Io was embedded in a dense plasma of sulfur and oxygen ions, evidently sputtered from Io's surface and atmosphere by magnetospheric particle bombardment. Ultraviolet observations revealed glowing clouds of sodium, potassium, and oxygen surrounding Io and extending along its orbit. These neutral clouds, created by atmospheric escape and sputtering, provided evidence for the continuous loss of material from Io to space. The Voyager measurements indicated that Io was losing approximately 1 ton of material per second, making it the primary source of particles in Jupiter's magnetosphere. The discovery of Io's thin atmosphere came from multiple lines of evidence gathered by Voyager. Observations of auroral emissions indicated the presence of sulfur dioxide and atomic oxygen. Radio occultation measurements, as Voyager 1 passed behind Io, suggested an ionosphere extending several hundred kilometers above the surface. The detection of a post-eclipse brightening as Io emerged from Jupiter's shadow provided evidence for atmospheric condensation during eclipse and subsequent resublimation in sunlight. Voyager's images revealed the first detailed views of Io's mountains, including structures rising 10 kilometers or more above the surrounding plains. These mountains appeared to be tilted crustal blocks rather than volcanic constructs, suggesting that Io experienced significant tectonic activity in addition to volcanism. Some mountains showed evidence of massive landslides, with debris aprons extending tens of kilometers from their bases. The global distribution of volcanic centers mapped by Voyager showed interesting patterns that would puzzle scientists for decades. Volcanic activity appeared concentrated at low to mid-latitudes, with fewer active centers near the poles. There also seemed to be a concentration of hotspots in the sub-Jupiter and anti-Jupiter hemispheres, potentially related to patterns of tidal heating. These distributions provided crucial constraints for models of Io's interior structure and heat transport. Galileo mission's revolutionary discoveries. December 7, 1995, marked the beginning of a new era in Io exploration as the Galileo spacecraft entered orbit around Jupiter, initiating an 8-year mission that would transform our understanding of the Jovian system. Unlike the brief flybys of the Voyager spacecraft, Galileo would make repeated close passes of Io, observing the Moon under varying lighting conditions and monitoring changes in volcanic activity over extended periods. The spacecraft's sophisticated instruments, including a high-resolution camera and near-infrared mapping spectrometer, would reveal Io's dynamic nature in extraordinary detail. The Galileo mission design presented unique challenges for Io observations. The intense radiation environment near Io's orbit posed significant risks to the spacecraft's electronics, limiting the number of close flybys that could be safely attempted. Mission planners carefully balanced scientific objectives with spacecraft safety, ultimately executing 6 close Io encounters, along with numerous more distant observations. Each close flyby was meticulously planned to maximize scientific return while minimizing radiation exposure. Galileo's first close encounter with Io occurred on December 7th, 1995, the same day the spacecraft entered Jupiter orbit. Passing within 897 kilometers of Io's surface, Galileo obtained images with resolutions as fine as 20 meters per pixel, revealing surface details invisible to Voyager. These images showed a landscape dominated by volcanic features, including active lava flows, calderas with dark floors suggesting recent eruptions, and mountains with layered slopes indicating a complex geological history. The discovery of extremely high-temperature volcanism on Io ranks among Galileo's most significant findings. The near-infrared mapping spectrometer detected thermal emissions from active lava flows with temperatures exceeding 1400 degrees Celsius and possibly reaching 1600 degrees Celsius or higher. These temperatures, comparable to or exceeding those of terrestrial basaltic eruptions, definitively established that Io's volcanism involves silicate magmas rather than just sulfur compounds, as some researchers had proposed. At the Pilon Volcanic Center, Galileo documented one of the most powerful eruptions ever observed in the solar system. Between observations in April and September 1997, a massive eruption at Pilon deposited dark pyroclastic material over an area of roughly 400,000 square kilometers, larger than the state of California. Temperature measurements during the eruption indicated lava temperatures possibly exceeding 1700 degrees Celsius, among the highest volcanic temperatures measured anywhere. The Galileo mission revealed that Io's volcanic activity exhibited both persistent and episodic behavior. Some volcanic centers, like Prometheus and Amirani, maintained relatively steady eruption rates throughout the mission. Others, such as Loki Patera, showed periodic variations in activity with characteristic timescales. Still others erupted violently and then remained quiescent for extended periods. This diversity of eruptive styles suggested complex subsurface magma storage and transport systems. High-resolution imaging of active lava flows provided insights into eruption mechanisms and lava properties. At the Prometheus volcano, Galileo tracked the advance of an insulated lava flow that had travelled roughly 95 kilometres from its source since the Voyager observations 18 years earlier. The flow advanced through a mechanism of breakouts from a cooled insulating crust, similar to terrestrial Pahoho flows, but on a much larger scale. Galileo's observations of Io's mountains revealed structures even more impressive than Voyager had shown. Some peaks reached heights of 17 kilometres or more, rivaling the tallest mountains in the solar system. Detailed images showed that many mountains consisted of tilted blocks of layered material, possibly representing sections of Io's crust that had been uplifted and rotated. The presence of these layers suggested that Io's crust preserved a record of past volcanic deposits, despite the rapid resurfacing rate. The spacecraft's magnetometer revealed the presence of an internal magnetic field at Io, though much weaker than those of other Galilean satellites. This field, roughly 1/10 the strength of Ganymede's, appeared to be induced by Jupiter's rotating magnetic field rather than generated by an internal dynamo. The characteristics of this induced field provided constraints on Io's internal structure, suggesting the presence of a partially molten region beneath the crust that could conduct electrical currents. Galileo made detailed observations of volcanic plumes, capturing them from various angles and lighting conditions. The spacecraft observed plumes reaching heights of 500 kilometers, with particles following precise ballistic trajectories predictable from Io's gravity and the initial ejection velocities. Some plumes showed complex filamentary structures, suggesting variations in particle size or ejection angle. The Tvastar plume, observed during a 2001 flyby, displayed a spectacular curtain of material erupted from a fissure 25 kilometers long. The mission provided the first detailed observations of Io's polar regions, areas difficult to observe from Earth or during the Voyager flybys. These observations revealed that volcanic activity was indeed less common at high latitudes, supporting models of tidal heating that predicted maximum heat generation at low latitudes. The polar regions also showed enhanced deposition of sulfur dioxide frost, creating brighter surfaces that might act as cold traps for sublimating volatiles. Monitoring of Io throughout Galileo's 8-year mission revealed how volcanic activity reshaped the surface on timescales of months to years. New lava flows covered hundreds of square kilometers. Volcanic plumes deposited fresh materials in vast ring patterns, and some mountains showed evidence of ongoing uplift or collapse. The global resurfacing rate, estimated at roughly 1 centimetre per year, was directly observed through these surface changes. Galileo's near-infrared mapping spectrometer provided unprecedented data on the composition and temperature of Io's surface materials. The instrument detected absorption, features diagnostic of sulfur dioxide frost, various sulfur allotropes, and possibly silicate minerals. Temperature maps revealed the thermal structure of active volcanic centers, showing hot cores surrounded by cooler flows and pyroclastic deposits. These observations helped establish the relationship between surface color and composition. The distribution of sulfur dioxide of frost across Io's surface, mapped in detail for the first time by Galileo, revealed complex patterns related to volcanic activity and atmospheric dynamics. Extensive equatorial deposits of sulfur dioxide frost appeared stable over multi-decade timescales, while volcanic hotspots created sulfur dioxide free zones, where high temperatures promoted rapid vaporization. The spacecraft detected a weak spectral feature at 3.15 micrometers, suggesting the presence of hydroxide, hydrate, or water-containing compounds unexpected on this dry volcanic world. During the October and November 1999 and February 2000 flybys, Galileo made its closest approaches to Io, passing within just a few hundred kilometers of the surface. These encounters, while risky due to radiation exposure, provided the highest resolution images and spectra ever obtained of Io. The near-infrared mapping spectrometer observations during these flybys mapped the detailed thermal structure of active volcanic regions and investigated an unidentified compound showing an absorption feature at approximately 1 micrometer wavelength. The discovery of active lava lakes on Io represented another major achievement of the Galileo mission. At Loki Patera, repeated observations revealed a lava lake undergoing periodic overturning events. The spacecraft observed waves of resurfacing propagating across the 200-kilometer-wide Patera at speeds of 1 to 2 kilometers per day. During these events, cool crust would founder into the underlying magma, exposing fresh, hot lava that would then cool and form new crust. This behavior, unprecedented in planetary volcanism, suggested a delicate balance between heat supply from below and cooling from above. Galileo's particle and fields instruments revealed new details about Io's interaction with Jupiter's magnetosphere. The spacecraft directly sampled the plasma environment around Io, measuring the composition, density, and temperature of ions and electrons. These measurements confirmed that Io was the primary source of particles in Jupiter's magnetosphere, with sulfur and oxygen ions dominating the plasma composition. The detection of molecular ions like SO+ and SO2+ provided insights into the ionization and dissociation processes occurring in Io's atmosphere. The mission documented dramatic changes in volcanic activity over its 8-year duration. The Tvashtar-Katina region, relatively quiet during early mission observations, erupted spectacularly in November 1999, producing a curtain of fire 25 kilometers long and a plume reaching 385 kilometers in altitude. The Surt volcano, which had shown no activity during the Voyager encounters, produced a massive eruption in 2001 that was among the most powerful ever observed in the solar system. Galileo's observations of Io's mountains in varying lighting conditions revealed their complex geology. Many mountains showed evidence of layering, suggesting they consisted of stacked volcanic deposits that had been uplifted and tilted. Some mountains appeared to be actively growing, with fresh scarps and landslide deposits indicating ongoing tectonic activity. The distribution of mountains concentrated away from major volcanic centers suggested a relationship between volcanic loading and tectonic uplift. The spacecraft's repeated observations allowed scientists to track the evolution of individual volcanic centers over time. At Prometheus, the steady advance of the lava flow created a moving source for the volcanic plume, causing the plume deposit to form an elongated track rather than a circular ring. At Amirani, the largest active lava flow field on Io, new breakouts and channel switching were observed between successive observations, demonstrating the dynamic nature of these volcanic systems. Galileo provided the first detailed observations of Io during eclipse by Jupiter, revealing how the moon's appearance changed when solar heating was removed. Auroral emissions from atmospheric oxygen and sulfur became visible, powered by the interaction with Jupiter's magnetosphere. The rapid cooling of the surface during eclipse, dropping by tens of degrees in just minutes, demonstrated the importance of solar heating in maintaining Io's tenuous atmosphere through sublimation of surface frosts. The mission's observations of volcanic plumes from multiple angles and at different times provided insights into eruption dynamics. Some plumes showed remarkable stability, maintaining similar heights and shapes over periods of months to years. Others varied dramatically, with plume heights changing by factors of 2 or more between observations. The largest plumes, reaching heights of 500 kilometers, launched material at velocities exceeding 2 kilometers per second, approaching half of Io's escape velocity. Analysis of color changes on Io's surface between Galileo observations revealed the rapid pace of surface modification. Fresh volcanic deposits initially appeared dark, but gradually brightened as they accumulated coatings of sulfur and sulfur dioxide from volcanic plumes and atmospheric deposition. The rate of this brightening provided constraints on the flux of materials through Io's atmosphere and the efficiency of volatile transport from volcanic sources to the surface. Modern observations and ongoing research. The conclusion of the Galileo mission in September 2003 marked not an end, but a transformation in how we study Io, as ground-based telescopes equipped with adaptive optics and space-based observatories continue to monitor this dynamic world. The 21st century has brought remarkable technological advances that allow Earth-based observers to achieve resolutions approaching those of spacecraft, while missions to other destinations have seized opportunities to observe Io in passing, adding to our growing understanding of the solar system's most volcanically active body. The development of adaptive optics systems for large ground-based telescopes revolutionized Io observations from Earth. These systems, which use deformable mirrors to correct for atmospheric turbulence in real time, allow telescopes like Keck, Gemini, and the Very Large Telescope to achieve near diffraction-limited resolution in the infrared. With these capabilities, astronomers can now detect and monitor individual volcanic hotspots on Io from a distance of 600 million kilometers, tracking eruptions and measuring temperatures with remarkable precision. The Keck Observatory in Hawaii has maintained a particularly intensive monitoring program of Io's volcanic activity. Using the facility's 10-meter telescopes equipped with adaptive optics, researchers have created a nearly continuous record of volcanic eruptions spanning more than 2 decades. This long-term dataset reveals patterns in volcanic activity that would be impossible to discern from spacecraft snapshots alone. Some volcanoes show remarkable periodicity, while others erupt randomly. The most powerful eruptions, termed outburst eruptions, occur roughly once per year and can briefly outshine all other volcanic activity on Io combined. In February 2007, the New Horizons spacecraft, en route to Pluto, made distant observations of Io during its Jupiter Gravity Assist maneuver. Despite passing no closer than 2.3 million kilometers from Io, the spacecraft's long-range reconnaissance imager captured spectacular images of a massive volcanic plume erupting from Tvashtar Katina. The plume, reaching 330 kilometers above Io's surface, demonstrated that Io's volcanic activity remained as vigorous as ever, nearly 3 decades after its discovery. The Hubble Space Telescope has provided unique contributions to Io science through its ability to observe in ultraviolet wavelengths blocked by Earth's atmosphere. Hubble observations have tracked changes in Io's atmospheric composition and density, detected auroral emissions powered by the interaction with Jupiter's magnetosphere, and monitored the distribution of sulfur dioxide frost across the surface. Long-term Hubble monitoring has shown that some surface features, particularly large sulfur dioxide deposits, remain stable for decades, while others change dramatically. The Juno mission, which entered Jupiter orbit in July 2016, has provided new perspectives on Io, despite focusing primarily on Jupiter itself. Juno's orbit, which passes over Jupiter's poles, allows unique viewing angles of Io and the other Galilean satellites. The spacecraft's infrared camera, GIRAM, has detected numerous volcanic hotspots and created thermal maps of Io's polar regions, areas difficult to observe from Earth or from spacecraft in equatorial orbits. Ground-based spectroscopy has revealed new details about Io's surface composition and atmospheric chemistry. High-resolution spectrometers on large telescopes can detect trace species in Io's atmosphere, including sodium chloride, potassium chloride, and various sulfur compounds. These observations suggest that Io's volcanic gases include species derived from the Moon's interior, providing insights into the composition of the mantle and the chemistry of volcanic processes. Radio observations of Io have opened another window into this moon's properties. The Atacama Large Millimeter Array, or ALMA, has detected thermal emission from Io's surface and atmosphere at millimeter wavelengths. These observations can probe beneath the surface to depths of several centimeters, revealing subsurface temperature gradients. ALMA has also detected molecular emissions from sulfur dioxide, sulfur monoxide, and sodium chloride in Io's atmosphere, mapping their distributions with unprecedented detail. The study of Io's plasma torus from Earth continues to provide insights into the Moon's contribution to Jupiter's magnetosphere. Spectroscopic observations detect emissions from various ionization states of sulfur and oxygen, allowing researchers to track changes in torus composition and temperature. These observations have revealed that the torus properties vary on multiple timescales, from hours to years, reflecting variations in Io's volcanic activity and atmospheric escape rate. Stellar occultations, events where Io passes in front of distant stars, provide unique opportunities to probe Io's atmosphere. By measuring how starlight dims as it passes through different parts of the atmosphere, astronomers can determine atmospheric density, temperature, and composition as functions of altitude. Recent occultation observations have revealed that Io's atmosphere is more extended and variable than previously thought, with significant asymmetries between day and night sides. Computer modelling of Io's interior, volcanism, and orbital evolution has advanced significantly with increased computational power. Three-dimensional models of tidal heating now incorporate realistic rheologies and can predict the distribution of volcanic activity based on different interior structures. These models are tested against the observed distribution of hotspots, providing constraints on properties like the thickness of Io's lithosphere and the extent of partial melting in the mantle. Laboratory experiments under conditions relevant to Io have provided crucial data for interpreting observations. High-temperature experiments with sulfur and silicate materials reveal how different compositions behave during volcanic eruptions. Studies of sulfur allotropes show how their colours and stabilities depend on temperature and cooling rate, explaining much of Io's spectacular coloration. Experiments on tidal dissipation in partially molten rocks help constrain models of Io's interior heating. The discovery of volcanic activity on other solar system bodies has placed Io in a broader context of comparative volcanology. The nitrogen geysers on Neptune's moon, Triton, the water plumes of Saturn's moon, Enceladus, and the possible water plumes of Jupiter's moon Europa represent different expressions of geological activity driven by various energy sources. Io remains the most extremely volcanic, but these other active worlds help us understand the range of geological processes possible in the outer solar system. Machine learning techniques are now being applied to the vast archives of Io observations accumulated over 4 decades. Algorithms can automatically detect volcanic eruptions in infrared images, track surface changes over time, and identify patterns in volcanic activity that might escape human notice. These techniques are particularly valuable for processing the continuous stream of data from ground-based monitoring programs. International collaboration has become essential for maintaining continuous observations of Io. When Jupiter is poorly placed for observation from one hemisphere, observatories in the other hemisphere continue monitoring. This global network ensures that major eruptions are not missed and provides the temporal coverage needed to understand Io's long-term behaviour. Data sharing agreements allow researchers worldwide to access observations regardless of which facility obtained them. Future exploration and Io's role in understanding other worlds. The future of Io exploration promises revolutionary advances in our understanding of this remarkable moon, with multiple missions in development that will provide unprecedented views of its volcanic activity, interior structure, and interaction with Jupiter's magnetosphere. These upcoming missions, combining close flybys with long-term monitoring, will address fundamental questions about tidal heating, volcanic processes, and the evolution of planetary bodies that current observations cannot fully answer. The Europa Clipper mission, scheduled for launch in October 2024, while primarily focused on investigating Europa's potential habitability, will provide valuable observations of Io during its tour of the Jupiter system. The spacecraft's suite of instruments, including high-resolution cameras, thermal imagers, and spectrometers, will monitor Io's volcanic activity from various distances. These observations will bridge the gap between the Galileo mission and future dedicated Io missions, maintaining our record of how volcanic activity changes over decades. The Jupiter Icy Moons Explorer, or JUICE, developed by the European Space Agency and launched in April 2023, will arrive at Jupiter in 2031. Although JUICE will focus primarily on Ganymede, Europa, and Callisto, it will make distant observations of Io throughout its mission. The spacecraft's instruments will monitor volcanic eruptions, study the plasma environment around Io, and investigate how material lost from Io affects the entire Jupiter system. The proposed Io Volcano Observer mission, currently under study by NASA, represents the most ambitious plan for exploring Io since Galileo. This mission would place a spacecraft in orbit around Jupiter with a trajectory optimized for repeated Io flybys. Over a baseline mission of 4 years, the spacecraft would conduct at least 10 close encounters with Io, passing within 100 kilometers of the surface while maintaining a safe distance from Jupiter's most intense radiation. The scientific objectives of a dedicated Io mission would address fundamental questions about this moon's geology, interior, and evolution. High-resolution imaging would reveal surface changes at scales of meters, allowing scientists to observe lava flow emplacement, plume deposit accumulation, and mountain formation in unprecedented detail. Thermal imaging would map the global heat flow, identifying all active volcanic centers and measuring their temperatures and power outputs. Understanding Io's interior structure remains a primary goal for future exploration. Gravity measurements during close flybys would determine the size and state of Io's core, the extent of melting in the mantle, and the thickness of the lithosphere. Magnetic field measurements would search for an internally generated field or better characterize the induced field, providing constraints on the conductivity and therefore the melt fraction of the interior. The composition of Io's lavas holds clues to the moon's formation and differentiation history. Future missions equipped with advanced spectrometers could determine the mineralogy of fresh lava flows, distinguishing between different types of basalt and potentially identifying exotic compositions. These measurements would reveal whether Io's mantle composition is similar to terrestrial planets or has been modified by billions of years of volcanic processing. Monitoring Io's atmosphere in detail would reveal how volcanic gases are processed and lost to space. Future missions could directly sample the atmosphere during close flybys, determining the abundance of trace species and isotope ratios. These measurements would constrain models of atmospheric chemistry and escape, improving our understanding of how Io has evolved over solar system history. The study of Io has implications extending far beyond this single moon, informing our understanding of planetary processes throughout the universe. Tidal heating, the mechanism powering Io's volcanism, likely operates in many exoplanetary systems, particularly around planets orbiting close to their stars, or in multi-planet systems with orbital resonances. Understanding how tidal heating works in Io helps us predict which exoplanets might be volcanically active and how this activity might affect their potential habitability. Io serves as a natural laboratory for studying extreme volcanism that would be impossible to investigate on Earth. The scale and intensity of eruptions on Io may be similar to those that occurred on Earth during its early history, when heat flow was much higher. By studying Io's volcanism, we gain insights into processes that shaped the terrestrial planets billions of years ago, but left few traces in the geological record. The interaction between Io and Jupiter's magnetosphere provides a unique example of moon-planet electromagnetic coupling that may occur in other planetary systems. Hot Jupiters, massive exoplanets orbiting close to their stars, might have moons experiencing similar interactions with their parent planet's magnetic field. Understanding the Io-Jupiter system helps us predict the observational signatures of exomoons and their potential detectability. Future technology developments will enhance our ability to study Io from Earth. The next generation of extremely large telescopes with mirrors 30 to 40 meters in diameter will achieve resolutions sufficient to map Io's surface in detail and potentially observe individual lava flows. Advanced adaptive optics systems will allow these telescopes to operate near their theoretical resolution limits, providing nearly continuous monitoring of volcanic activity. Space-based telescopes of the future will offer unique capabilities for Io observations. The James Webb Space Telescope, with its unprecedented infrared sensitivity, can detect and characterize volcanic hotspots with greater precision than ever before. Future ultraviolet telescopes could map Io's atmospheric emissions and study how volcanic gases are dissociated and ionized by radiation. The development of radiation-hardened electronics will enable future spacecraft to survive longer in Io's harsh environment. Advanced shielding techniques and fault-tolerant designs could allow missions to make more frequent close passes of Io, gathering data from within the most intense regions of Jupiter's radiation belts. These technological advances might eventually enable a landed mission to Io's surface, though the challenges of surviving both the radiation and volcanic activity remain formidable. International cooperation will be essential for the comprehensive exploration of Io. The scale and complexity of missions to the outer solar system increasingly require resources and expertise from multiple space agencies. Collaborative missions, combining instruments and technologies from different nations, can achieve scientific objectives beyond the reach of any single agency. The search for volcanic activity elsewhere in the solar system continues to reveal new targets for comparative studies with Io. Recent evidence for possible ongoing volcanism on Venus, ancient volcanic plains on Mercury, and cryovolcanism on numerous icy moons expands our understanding of the various ways planets and moons can remain geologically active. Io remains the most extreme example, but each active world provides unique insights into planetary processes. Educational and public outreach efforts centered on Io help inspire the next generation of planetary scientists. The dramatic volcanic eruptions, colorful surface, and dynamic nature of Io capture public imagination in ways that static, cratered worlds cannot. Virtual reality experiences, real-time eruption tracking websites, and citizen science projects involving Io observations engage people worldwide in the exploration of this remarkable moon. The preservation and analysis of decades of Io observations represent a crucial aspect of ongoing research. Digital archives containing data from Voyager, Galileo, ground-based telescopes, and Hubble must be maintained and made accessible to researchers. As new analysis techniques emerge, these historical datasets can yield discoveries not possible with the technology available when the data were first obtained. Climate modelling techniques developed for Earth are being adapted to understand Io's atmospheric dynamics. These models must account for the unusual properties of Io's atmosphere, including its dramatic day-night variations, the influence of volcanic plumes, and the continuous loss to space. Successfully modelling Io's atmosphere advances our understanding of atmospheric physics under extreme conditions. The role of sulfur chemistry in Io's volcanism provides insights relevant to early Earth and potentially to Venus. Sulfur plays important roles in volcanic gases and climate on terrestrial planets, but nowhere is it as dominant as on Io. Understanding how sulfur behaves in Io's volcanic systems helps us interpret sulfur isotope records in Earth's oldest rocks and predict how sulfur might affect the evolution of Venus-like exoplanets. Astrobiological implications of Io's volcanism, while not directly related to life on Io itself, inform our understanding of how volcanic activity might affect habitability elsewhere. The continuous supply of chemicals and energy from volcanism, the processing of surface materials, and the maintenance of atmospheres through volcanic outgassing are processes relevant to potentially habitable worlds. While Io is far too hostile for life as we know it, the principles learned from studying its volcanism apply to more benign environments.